Okay, today we're going to talk about key features from the vertex form of a quadratic. I hope that you've already kind of read through and started this. The purpose of this investigation is to help you guys relate what we already know with absolute value functions to quadratic functions. And I know that if you kind of go through this and like make some of these connections on your own, it'll help you to be able to like solidify those connections. Sometimes if I just tell you all of them, they don't solidify as well. So I would try it a little bit on your own. See if you can see some similarities, some differences, and those aha moments are kind of the things that stick. And then again, I've posted the key, and then you can kind of walk through this. I'm just going to walk through parts of this and show you kind of where we're headed with this. The very first thing on this is our goal here is that we will be able to actually apply what you know about vertex form. So apply knowledge, that says knowledge of absolute value functions to quadratics. Yikes, this is going to be a long one in vertex form. So the reason we're going to start with vertex form is because vertex form actually looks like the absolute value function. So if you come down here, you'll notice the first thing it asks you to do is draw the graphs of both of the functions. So you can use a calculator if you need to, but this is an absolute value function, so we should be pretty good with that, right? We know that this means it shifted down 5, this moved the vertex left 4, so our vertex is at the point -4, 5, and then this gave us our slope, right? It's reflecting down over the x-axis with a slope of 1. So we could go to the left 4, we'd go down 5, that's where our vertex is going to be. And then again, we've got a slope of 1 there, so we can graph this absolute value function going down. And then the goal there is, notice that here's our quadratic now. This is very, very similar, but instead of absolute value bars, you've got parentheses squared. So this means it's a quadratic function. It has a degree of 2. And you'll notice if you were to graph this on your calculator, the behavior is very much the same. So I hope you did go ahead and graph it and look at this one also goes down 5 and it goes to the left 4. So if I graph the vertex, I'm going to do this one in blue, it actually is sitting at the same point as the vertex of the absolute value function. So they work identical. This also means that it's going to open down, so it's been reflected down. Now the only difference here is this does not have a linear slope. So because it's a quadratic, it has a slope of perfect squares, right? So we talked about in class last time that it's going to go over 1, up 1. If you're 1 unit away from the vertex, in the left or right direction, it's 1 unit up. If you're 2 units away, it's 4 units up because we're looking at a quadratic that increases by perfect squares. Oh, I missed. So then you would connect those with like a U-shaped graph, right? We know that this is going to create a U-shaped graph. So it says compare and contrast, state at least one way in which the functions are similar and at least one way they are different. I hope you kind of think through that. So notice some similarities that you could write down would be that they have the same vertex. So they share the same vertex. Another thing, if you're looking at their equations, one of the biggest differences, right, is this first one has absolute value bars. And so its graph creates a V. This one has a quadratic or a degree of 2. So this guy's creating a U shape, right? Another similarity, they're both opening down. They've both been reflected. So all of these different things, we want to recognize some similarities there and some differences. And then you're going to do the same thing as you graph this one down here. So some similarities, or sorry, just graphing this one. Again, our vertex, right, it goes to the right 3 and then it goes down 4. And then notice this slope of 2 out front. So I'm going to go over 3, I'm going to go down 4, and that's my vertex. I then have a slope of 2. So I'm going up 2, over 2 in each direction. And I'm just going to get just enough of that graph to be able to tell where it's headed. And then I can graph the g of x. So I'm going to label this one f of x, so I remember that's my absolute value function. G of x, notice it's the same idea. So down 4 to the right 3, so the vertex is in that same spot. This time though, we have a quadratic, right? So we're going to move by perfect squares, and then we're going to actually double it. So remember, perfect squares would be 1 unit away is 1, 2 units away is up 4 units. So everything is going to get doubled. Instead of being at 1, 1, it's going to be up at 2 because that's double. Instead of being up 4 units here, we're going to be up at 8. So it's going to stretch it much taller than before. Again, if you need to graph this on the calculator, that's fine too. 1, 2, 3, 4, 5, 6, 7, 8. So we're here, and we just make sure that it is symmetric here, and we do our best to draw a U shape. And then some of the similarities and differences between these key features. So here's g of x, here's f of x. Let's define some of these key features. We noticed that they had the same vertex. They're both at 3, -4. So that's one of the coolest things as we move to this vertex form of a quadratic, is we already know how to deal with that vertex and those transformations. The axis of symmetry, remember, is the line that just divides this graph perfectly in 2 symmetric halves. So that would cross at x equals a +3, and it always goes through that vertex, right? So it's just the x value of the vertex. And notice we could find that axis of symmetry just by looking at the equation. It's always that h value because it has to go through that vertex. The y-intercept, you can see on the blue graph that the y-intercept is crossing this y-axis at a +2. So that one's pretty easy to see from the graph, the point 0,2. The other one's a little bit harder. Because it's a quadratic, it's increasing so fast. So if all else fails, you let x equal 0 to find a y-intercept. So I'm going to take this g of x function, and I'm going to basically evaluate it for 0. So I'm going to do 2, and I'm just going to put 0 in for x. And as we do that, we get 2, and we get -3 squared, because 0 minus 3 is just -3. When you square a negative, -3 times -3 is +9. So this is going to be 18 minus 4, or in other words, 14. So our y-intercept down here is definitely different than the other y-intercept, right? They're increasing at different rates. Domain, we know, was always -infinity to infinity, or all real numbers. It remains the same on a quadratic, so it's headed in both directions. Everything works within this function. The range, also very similar to our absolute value. Notice the range, our y values, right, always stay above -4. So it's -4 up to infinity. Or again, if you would like to write y is greater than or equal to -4, that works too. The increasing, decreasing, this was kind of the newer one as far as there were 2 halves to it. So we had our axis of symmetry, and then we looked to see if it's increasing or decreasing on the left or the right-hand side. Notice this graph moving left to right is going down first, then it reaches the minimum, then it comes back up. So on the left side of the graph over here, we're decreasing, and on the right side, we are increasing. So we can write this 2 ways. We're decreasing on the left side of the axis of symmetry, or when x is less than 3, right? And that's true for both of these. Oh, not that though. Both of them are decreasing on the left. And then that means that they reach that low point and they increase on the right of the axis of symmetry. So you can write it that way, or if you like to write it as like -infinity over to 3, you can write it that way too, and then 3 to infinity. So whichever way you like it better on that. And then max and min, we can see that this graph has a minimum at the bottom of the graph. Oh, that's the word min. And notice the minimum value this graph ever reaches is -4. So it has a minimum of -4, and that always matches that range. So the goal there is, if you can kind of look at these and compare them, really the only ones that are going to be different is like your y-intercepts, because that slope's running differently. Other than that, they behave very much the same way as far as identifying pieces of them. So we could do this without the use of a calculator and having to graph. I'm going to kind of just work through the first one. You'll go through and make sure the second one's done as well. You can check it with the posted key. So on this first one, again, remember the vertex comes from this h and this k. So we do the opposite, right? It moved right 2 and it moved up 5. So our vertex is at 2, 5. The axis of symmetry, we know, goes right through that vertex. So we use the x value of the vertex to write our axis of symmetry. Y-intercepts occur when x is 0. So I'm going to write this just off to the side. When x is 0, that means that y would be equal to, and I'm going to put a 0 in where x is, and simplify. So that's -2 squared plus 5, which is 4 plus 5, which is 9. So my y-intercept here is 0, 9. Domain remains the same. All real numbers are negative infinity to infinity. Your range, you need to figure out if it's opening up or down. So remember, we look out front to see if it's been reflected or not. There's no negative value out there, so this one is opening up. And I always just draw a little picture just to help me keep track. So the range is going to start at that 5 value, right, the bottom of my vertex, and it's going to go up forever. So you can write it that way, or again, you can write y is greater than or equal to 5. Okay, increasing and decreasing. Notice this guy. There's my axis of symmetry. He's decreasing on the left, so he's coming down before he then goes back up. So this is decreasing first. So again, we're going to say x is less than 2, or on the left side, or again, if you'd like to say negative infinity to 2, it's decreasing. Then it starts to increase on the right of that axis of symmetry, so from 2 to infinity. Again, this one's opening up, so it has a minimum, and that minimum of 5 relates to our range there. So really important that we're just able to identify the pieces that we recognize this is quadratic, but it works a lot like an absolute value function. On the next part, you're writing quadratic functions. So we just are trying to see if we can go backwards. So write a quadratic function in vertex form. Again, it's going to look something like this, right? And graph that. Just sketch a graph that satisfies the following. So first of all, vertex is at 2 and 3. So remember, vertex just goes right into our function right here and right here. So if I want to write this equation, right, I know that it's going to be a squared because it's quadratic. That 2 is just going to sneak right in here, and we're going to change the sign on the 2, and the 3 is our k value, so we put plus 3. Then I can put x, and I can put y is equal to. Now, I could put a different a value if I wanted to. Notice that vertex would stay the same. As long as I don't put anything in the parentheses, right, that would stay the same. I could put whatever I wanted out here. And I'll show you what that kind of looks like on the graph. So if we take this one, let's say we just sketch a graph. So sketch means we need to have a few points that are in the right spot. It needs to look the right shape, but doesn't have to be perfect. So on this one, we sketch our vertex is at 2, positive 3. And notice I didn't put a negative out front, so my graph should be opening up. Okay. Now, the question right after says, how many different parabolas could be drawn that have that same vertex? Well, if you look at this, I could have stretched this out a little bit, and I could have drawn it like this, right? I could stretch it this way. I should have said shrunk before. We could draw another one over here. We could flip some over and draw some here. We could stretch them down here. They all have the same vertex, right there. So there are actually infinitely many parabolas that we could draw through that same vertex. Now, as we go down, they get a little bit more specific. So the next one says, what about if the vertex is at negative 2, 3, and the range is negative infinity up to 3? So the reason this one's a little more specific is our function, right? If we go to put it in, we know it's squared. We put in the h value, which is a positive 2. We put in the k value, which is plus 3. And then we put in our x and our y. Now notice the range here is negative infinity to 3. So that means it has to be one that's upside down because it's negative infinity up to 3 and it stops. So in this case, we want to put a negative out front. Okay, that would complete that equation. And then when I go ahead and graph it, I just want to make sure that I plot that vertex, negative 2, 3. And then it's upside down, so I'm going to have it head this direction. Okay, again, just getting kind of an idea. Now again, the question is proposed, how many different parabolas could be drawn that have the same range and vertex? Well, I could draw one that was a little taller and skinnier. I could draw one that's a little wider. I just have to make sure they keep facing down so that they look or have the same range. But notice there are infinitely many parabolas that I could draw going down. So even though we got a little more specific, there are still infinitely many that could be drawn facing down. Now number 3 says a vertex is at negative 5, negative 1 and passes through negative 2, 2. Now this one again, here's our h and our k. So we could build most of our function going off of this. We could say plus 5 minus 1. And we want to make sure that's squared. And we have y is equal to. Now we need to make sure it goes through the right point. So if I was drawing the little graph over here, I'll just kind of sketch a little graph. It looks like it's going to the left 5 and then down 1. So there's my vertex. I'm going to put a little V by it. And it says it needs to pass through the point -2, 2. So it needs to pass through this point. So on the graph, I can kind of do that. I could extend this a little bit further and say, well, this point is like, to make it symmetric, right, over 2, up, it looks like 3. So I could go, oh, sorry, over 3. Over 3 this way and, you know, up here. So I can create kind of the picture of the graph. But the question is, that definitely has been shrunk. So I need an A value in here to make something a little bit different, right? I need a stretch or a shrink. So the way that we do that is we use the point to help us. So I'm going to take this equation that we built and I'm going to put an A value there, x plus 5 quantity squared minus 1. And we're going to use this point xy because we know that it's a solution that works in the equation. We're going to put 2 where the y is because my y value is 2. And we're going to put -2 where the x is from that point. Everything else stays the same. So again, we just used that point to plug in. Now notice we can solve for a. So I have 2 equals a. -2 plus 5, we start in the parentheses. Go ahead and add that 1 over so you don't accidentally combine it with the squared. So we get 3 equals a times 9, or in other words 9a. And then if we divide both sides by 9, we get 1/3. So the a value that works in this equation would be 1/3. Okay. Now if you think about it, it asks down here how many different parabolas could be drawn that have the same vertex and pass through that same point. Well, the answer now is 1. This is the only one. Because if I stretch it at all, it doesn't pass through that point. If I try and reflect it, it doesn't pass through that point. The only one, if I know the vertex and one other point, it makes it have to reflect that point and it gives us one unique or distinct parabola. Okay, so this is only one parabola can be made with those specific conditions. Okay, you're going to try the same thing on that next one. Build one with that vertex that passes through that point. So kind of follow that same procedure and see if you can build that function. Jumping down, so just practicing using function notation for transformations. If we are given different types of functions and we want to just transform them, I just want you to notice that it transforms very similar to an absolute value as well. We're just going to use more specific function notation. So this says write the function for h of x. So notice that h of x is referring to one of the other functions and then it's changing it a little bit. So if I take h of x is equal to, this wants me to use f of x. So I come up here and I find where f of x is and I just write in that equation. So x plus 1 squared minus 3. And then I want to add 5 on the end to that because that's what was happening on h of x. So when I rewrite this, everything stays the same except I have -3 plus 5, which is a positive 2. Okay. And you're going to do that on each one of those. And then again, you can check your answers with the key that's posted. Once you've done that, you're going to come down here and it's going to ask you to graph each of the function. And you're going to contain the original one. So for example, this one we used f of x. And then we're also going to do the new one that we transformed. So let's start with f of x. So notice f of x up here is equal to, or has a vertex of -1, -3, right? That h and that k. So I'm going to come over here and I'm going to go left 1, I'm going to go down 3, and I'm going to put my vertex right there. Notice the slope hasn't changed at all. It's not stretched or shrunk or reflected, so I'm going up by perfect squares on this one. 1 unit away from the vertex is up 1, 2 units away is up 4 because 2 squared is 4. 3 squared is 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're just making sure that it's symmetric there. Do the best you can, draw a little V shape here. Now again, this represents the function f of x, so let's label it. Whenever we're putting more than one function on a graph, it's good to label. Then we want to do the new function that we built, h of x. So notice this one, if I look up here, oh, I drew a terrible plus sign. The h of x here, the vertex is at -1, +2. So if I come down here, -1, +2, I'm up here now. And notice, again, it hasn't been stretched or shrunk at all. It just came up a little bit. So we're still going over 1, up 1, over 2, up 1, 2, 3, 4. And the next one's going to go off the graph, so I'm just going to use that many. Now you'll notice this function right here, if I was comparing these, it's just moved up. It hasn't stretched or shrunk, it just moved up, right? 1, 2, 3, 4, 5 units from the other vertex. So if we were comparing these, the only difference is that one shifted vertically 5, which makes sense because that's exactly what it was asking us to do, is to shift this one up 5. So you can tell if you look at like the next one, when you graph both of them, one of them is going to be flipped over and stretched by 2. The other one, if it's on the inside, right, moves left or right. So this one should move the graph left 3 from where it originally was. So you can kind of compare that. Again, use the key at the end or below this video to kind of help with that. Okay, complete the rest of this packet, work through it, make sure you're good with that. And then you can complete these textbook problems are kind of your additional practice. So there's a few, these come from section 3.4, and there should be room if you printed this just on the back side of this packet to complete these problems, okay? Again, good luck. Reach out if you have any